Oh yeah, our project is due tomorrow, right?
Yeah. Right. And then, so I wanted to say something about that. So I want you guys to be able to look at other people's projects and sort of and share your own. So I was thinking of making a discussion board on Canvas. So you'll need to turn in your project like your regular assignment, but I also want you to post it to the discussion board. Okay. And I will post some instructions for like uploading videos and just generally what I want you to do. So I do want you to turn it in two places. And if I don't see it in both places, I'll probably bug you about it. The other thing I wanted to announce was that I finally heard back about the final exam schedule, and it turns out there will not be a final exam schedule made this year. I guess I could have guessed that by now. But I think we will move ahead with essentially using our class time on Monday, but I want to go 30 minutes longer, so it should be 2 hours. So it will start at 12:30 and end at 2:30 on Monday. And the date is May 17th. So our final is May 17th from 12:30 to 2:30. And I'll also post that on Canvas so that you can look it up if you forget. Okay, so let's see. Let's get this started. Okay, let's see. It's good. Seriously? Wait, what happened? Okay. I'm still here. Okay. Okay, cool. So we are still on 6.2, right? So we are talking about orthogonal sets a little bit more. So we did define orthogonal sets last time. We talked about dot product and orthogonality. And we are going to first talk about projections and then define an orthogonal basis. Okay, so projections. So we're going to focus on the projection of one vector onto another. So we'll say the projection of U onto V. And this is going to be, so looking at a picture of, say we have U here and V here. The idea is that we want to basically figure out if we were to sort of smash U onto that vector V, what would that vector be? And it would be this guy right here in our picture, right? So say the angle between those is theta. So this is going to be just like very, what's the word I'm looking for? This is imprecise, but is going to be the part of U in the direction of V. Right? So we're going to use the notation PROJ, so projection of U onto V. So V is like a subscript of this right here, right? And that's what we're projecting onto. Okay, so here I've drawn this. This should be a right angle. Oh. So if we are looking at this picture, we have a triangle, right? We have a right triangle. So we can use some of the stuff that we know about triangles to write down a formula, right? So we know that the length of this side is going to just be the norm of U, right? Because that side is made up of that vector U. And so what we get is that this projection is going to be, well, its length is going to be so we have an angle here, so it's going to be norm of U times cosine theta, right? That's the length of that pink part. Is that part okay with everybody? Okay, cool. So that's the length, and we know that it should be going in the same direction as V, so we can create the unit vector in the V direction by taking V and dividing by the norm, right? We talked about this last time. This is a unit direction, unit vector, right? It just has length 1. And then if we multiply it by the length of the projection of U onto V, we get that vector there, right? So taking these two things and multiplying them together, we get that the projection, the actual vector, should be equal to U times cosine theta times that unit vector V over norm V, right? Okay, so we're gonna do some manipulation to be able to write down a nice formula for this. And so what I'm gonna do is take that norm of V and put it with the other, I guess this is a, oops. Oh my God, okay, here we go. Okay, I'm gonna put that norm of V with the other scalar part, right? So we'll have norm of U times cosine theta over norm of V times V. So this part is a scalar, right? And then we're multiplying by that by the vector V. Okay, now I can multiply the top and bottom of this fraction by the norm of V. So that I get norm of V squared in the denominator, right? And then does anybody recognize what this numerator is? We talked about this last time.
Is that U? Okay.
It is U dot V, yeah. This was the formula that we had last time for the dot product involving the cosine of the angle, right? So we get U dot V, and then in the denominator, we had last time that the norm of V squared is equal to V dotted with itself, right? So we get U dot V over V dot V and multiply that by the vector V, right? So this is the formula that you usually use to find the projection, right? So we don't usually use this formula. We go, because it's easier to compute the dot products and get this, right? Okay, so our formula, just to make it clear, is the projection of U onto V is U dot V divided by V dot V times the vector V. Okay, And then maybe we should do just a quick example. So if we had U equals 1, 2, 3, and V equals 4, 5, 6, let's say. Then the projection of U onto V, it's just, we just find it using the formula, right? So U dot V, we multiply the entries. Okay, so we have 4 plus 10 plus 18. And then in the denominator, we have V dotted with itself. So that's going to be 16 plus 25 plus 36. And then we multiply that by the vector V. And so I'll leave you to simplify this, but right, you can work out what this would be. Okay. Okay, so this is the projection. You can also see this as the projection onto the line that is defined by the vector V, which is just the span of that vector, right? So in the book, you'll see the notation, the projection onto L, where L is the span of V, which is just a line, which is why we use L for it. Okay. You can also define the projection in another way, which will come in handy a bit later. So you can also define the projection in the following way. And that is to say that the projection of U onto V is the vector such that U minus the projection is going to be in the span of V perp. That is the span of V as a subspace perp, right? So this is saying that if we take U, subtract off the projection, whatever we are left with should be perpendicular to V, right? So if we look at our picture again, so we have U and V. We know that this should be the projection right here, this vector. And we can get that by figuring out what vector we need to subtract off of U to end up with a new vector. We'll call it W, which will be in V perp, or the span of V perp. Right. Okay, so W is perpendicular to V. Right.
So is that dotted line the same thing as U minus projection VU?
The dotted line would be right, but just translate it over, because I guess here's our origin. So it's going to be the same length. I guess maybe I should draw it a little bit more carefully. Yeah. So U is equal to, you can see that it would be the sum of W and this projection. And so that's where we get U minus the projection is equal to W. Okay. So the reason why this is beneficial. The reason why we might want to define the projection in this way is because it will generalize to projections on higher dimensional subspaces. So we can think of this as projecting onto the subspace of the span of V, right? But this definition also works for higher dimensional subspaces because we can, for higher dimensional subspaces, define V, we'll say this is, we'll call this W. We can define W perp, right? For any subspace. So,
Pardon me.
yeah.
Sorry, I'm confused. Is W the span of V perp, or is W perp the span of V perp?
W perp is the span of V perp. So
Okay.
I meant to say that W is the span of V.
Okay, just trying to keep track.
Yeah.
Thank you.
Okay, so now we're going to, we'll come back to this idea in a second, but we need to define a couple of things. So the first is going to be an orthogonal basis. For a subspace W of Rn is going to be an orthogonal set that spans W. Okay, so remember that orthogonal sets, so an orthogonal set was just a collection of vectors where they were pairwise orthogonal. So if you took any two and compared them, any two distinct vectors and compared them, they would be orthogonal. And so we showed last time that orthogonal sets are linearly independent, right? So we automatically get that this orthogonal set is linearly independent. And if it also spans W, then it's a basis for W, right? So maybe I'll write this down. Call that orthogonal sets are linearly independent. So this is a basis. So an orthogonal set that spans W is a basis for W. Right? Okay. The other definition that we will have is an orthonormal basis. So this is going to be an orthonormal, there we go, okay. Basis is an orthogonal basis where all of the vectors are unit vectors.
Wait, what the normal? Okay.
Mhm. So they just all have length 1. And an example of an orthonormal basis is just the standard basis, right? The standard basis of Rn where we just have the coordinate vectors, E1 up to En. This is an orthonormal basis, right? Okay. All right, so we have orthogonal and orthonormal bases. And these are really nice because of the following theorem, which we will not prove. I guess I'll bring this out. But it is in the textbook. So this says that if, say, we have a basis, B1, or we'll use the same notation as, so we'll use U1 up to UK of a subspace W of Rn. So suppose this is a basis of a subspace W of Rn. Okay. Then for any vector in the subspace, in W, we can write out what the expression of that vector would be in terms of the basis vectors. So W we can write as a linear combination of the basis vectors, well, because it's in W, but we have a special expression for this. So, oops. So this is equal to some constants times the basis vectors, where we will be able to have a nice formula for these. So this is equal to this, where CI is going to be, W dot UI over UI dot UI, right? So this looks just like what we just saw was the projection, right? So this is the length of the projection of W onto UI, right? So what we have here, right, what we have here is just these are not exactly the projections onto each of these because we didn't have an orthonormal basis, so we didn't have length 1 for each of these vectors, but it is something close to that, right? So similar idea.
Well, I'm trying to figure out, does it work out like CI times UI becomes that W times UI over UI times UI, and then times UI, so that like that.
Yeah, it should work out. Yeah, you're right. So this would give you the projection.
But I'm not really sure what it means to say that C1 U1 is the projection of W onto U1.
Mm-hmm. Right. Okay, so let's just look at C1 times U1 in particular. So that's W dot U1 over U1 dot U1 times U1. So this is just the definition that we had for C1, right? And this is the projection of W onto U1. And that's from our formula up here, right? So this is our formula with U and V. Here we have instead W and U1.
Okay, so W is the sum of all the projections of UI, or all the projections of W onto each UI.
Yeah, exactly.
But like, what does that mean? Does it mean anything to say it in that way, or no, not really?
So you could think of like, I guess it's easiest to see this in Rn or R3, where you have just the standard basis, right? And if you wanted to represent your vector W, say you didn't know what it was in the regular coordinates, the idea is that you just, you can project it down onto one axis and that gives you the coordinate in that direction, right? And then you project it onto the other axis and that tells you the coordinate in the other direction, and then finally the last one. So I'll have trouble drawing that, so I'll stop here, but that's how you get those coordinates or the scalars in your linear combination. Is just by projecting it onto one of the vectors. That gives you the scalar that should be in front of that vector, and then you project it onto the next one and you get another scalar, right? Does that kind of make sense?
Yeah, mostly. This seems really convenient.
Yeah.
Wait, so for this theorem, the basis does not have to be orthogonal?
It does have to be orthogonal
Okay.
in order for this to work. Yeah. Okay, so let's see, we have this formula, and then notice that, so maybe I'll just put this in parentheses, that if furthermore your basis is, so if this basis is orthonormal, then what do you get? You get that the CI, so this is, we could rewrite this as W dot UI over the norm of UI squared, right? And so this will become, if these are orthonormal, then the norms are all one. And so this simplifies to just U or W dot UI. Right? Okay, cool. Let's see. Okay, so let's do an example. So one thing to notice is that if you get your, so these are basis vectors, right? And if you write them as a linear combination in this way, then you get, maybe I'll do a different color. This tells you that the representation of this vector W in the basis is going to be the vector where you take these coefficients and just stick them into a vector, right? And that was the definition of the coordinate vector. And we use this notation for that, right? Okay, so we're going to, so when we're asking in this question to find the coordinate vector where W is equal to 1, 2, 1, and this basis will be, let's see, 1, 0, 1, minus 1, 4, 1. Okay, so when we ask this question, we can use the previous theorem, right? Because it's going to tell us how to find those coordinates, and then we just stick them into a vector and we get the coordinate vector, right? So first of all, we would need to check that this is orthogonal, this basis. But we did this last time. You can double check again. You just need to take the dot product of each pair of vectors and see that those are all 0, right? But this basis is orthogonal. You can check by taking dot products of each pair, and there's only 3 possible pairs, right? So it's not too difficult or time consuming. Okay, so this theorem that we just had tells us that we can write W as C1 times this vector, the first one, C2 times the vector -1, 4, 1, and C3 times this last vector. And it'll be convenient to give these names. So we'll call this one V1, V2, and V3. Or maybe we'll use U since we were using U in the theorem. Okay, so this will be U1, U2, and U3. Okay. So the theorem tells us that C1 in this linear combination is going to be equal to W dot U1 over U1 dot U1, right? So I'm going to write out these vectors. Where is it? Okay, W is 1, 2, 1. And we're going to dot that with 1, 0, 1, divide by 1, 0, 1 dotted with itself. Right. So if we work out what this is, we get 1 plus 0 plus 1 in the numerator and the same thing in the denominator. So this is just going to be 1. And then we can do the same thing for C2. So we're going to take W dot U2 over U2 dot U2, which is here 1, 2, 1 dot -1, 4, 1 over this dotted with itself. And that will give us -1 plus 8 plus 1 over 1 plus 16 plus 1. So that's 8 over 18, which is 4 over 9. Right? And then we can do the last one. Maybe I'll let you guys do this yourself and you tell me what you get. Did anybody get an answer?
I got 4, 9.
That's what I got as
4
well.
over 9.
4 over 9?
Yeah, 4 over 9 again.
Interesting. I got 2 over 9.
Okay.
Did anybody get 2 over 9? Or let's just do it. Okay, So in this case, we get 2, 1 minus 2.
It is 2/9. You're correct.
It is, okay.
Sorry.
Yeah, you're
My
right.
bad.
Yeah.
I don't know how we all messed that up. That's kind of funny.
How was my brain? Like, oh yes, 2 + 2 - 2 is 4. I'm good at math.
Yeah.
No, it's just like a common mistake, I guess, that like most of our brains kind of function the same way.
Yeah, I guess so. Okay, cool. So we have an answer. And we can then write this as our C1 times U1. So that'll be just U1 plus 4/9 U2 plus 2/9 U3, right? Which means that the basis vector for W is 1 4/9 2/9, or the basis vector, the coordinate vector in B, right? Okay. Cool. So, right, this is how we go about finding these coordinates in this way. So this is actually a pretty useful theorem. We also have the following, which we will also not prove. This theorem it has to do with matrices that have orthonormal columns. And these are really nice, and they're actually very useful computationally. So a matrix, so when we say it has orthonormal columns, it just means that the columns are pairwise orthogonal. So if we compare them to each other, they're all orthogonal. And then also that that they have length 1, right? So a matrix with orthonormal columns, which I will write down what I just said. Okay. So if it has orthonormal columns, or no, a matrix with orthonorm, no, I mean, I want has here. A matrix has orthonormal columns if and only if we usually use U for this type of matrix. If and only if U transpose times U is equal to the identity. Okay, here we go. Right, so why is this the case? I guess this is kind of a proof, but so first, if you have that your matrix has columns U1 up to UK that are orthonormal, what this means is that if you take UI dotted with itself, well, that is just the norm of UI squared. And if it has length 1, that's just equal to 1, right? And otherwise, if you take UI dotted with UJ for any J not equal to I, you should get 0 because they're orthogonal. Right. And remember, so when we were first defining the dot product, we defined it in this way, where we take UI transpose times UI, right? That was the definition for the dot product. So this would be UI transpose times UJ. Okay, And so that means that if U is the matrix with these columns, so it's the matrix with the columns U1 up to UK, then U transpose is going to be U1. So I'm going to write it in this way. And what I mean by this is we're forming a matrix where these are the rows. These are row vectors, right? Because we took the transpose. So U2. Okay. So does it make sense what I'm trying to express there? So the rows are these vectors now. Okay. Then we can multiply these two together. So we want to see that U transpose times U is equal to the identity, right? That's what we're aiming for. So we take U transpose multiplied by U, which is going to be this vector here, U1 transpose up to UK transpose times this vector, which is U1 up to UK, right? Maybe I'll include one more actually, sorry. Okay. U2 up to UK, U1, U2 up to UK. Okay, so we should be able to see what happens here. So when we do this multiplication, remember this is a row vector. So let me circle this guy, and we're multiplying by this column vector, right? When we do the matrix multiplication. So we'll end up with, in the first entry, just U1 transpose times U1, right? That makes sense? Okay, and then in the second entry, we end up with U2 transpose times U1 transpose, sorry. U1 transpose times U2. And then this continues on, we get U1 transpose times UK. And then in the second row, we do the same thing. So we get U2 transpose times U1. And then we get U2 transpose times U2, and so on. And we keep going. And we end with UK transpose times UK. Okay, but as we said, these are just going to be the definition of the dot product of those two vectors that we're multiplying together. And like we also said, if I is not equal to j, so if we're multiplying to, in one of these entries, say here, where the indices are not the same on those vectors, that's going to be 0, right? Because they're orthogonal. But when we're multiplying ui transpose times ui, for instance, like here, we get 1. So you can see just by going through the matrix that you're going to get 1s on the diagonal and 0s everywhere else, which is the identity, right? Okay, so we can see that U transpose times U is equal to the identity. Is there a question?
Yeah, I know that matrix multiplication is not commutative, but if you had U times U transpose, would you also get the identity matrix?
Yeah, you would.
Okay.
Right. So you can check in the other direction. This should also work. Yeah. And that's because this is a nice matrix, right? And in fact, so if U is, notice if U is n by n, then U inverse is equal to U transpose, right? And this is actually, we can use this to be the defining property, which we will do in a second. But first, I wanted to go over properties of these types of matrices. So, okay, so if U is an M by N matrix, with orthonormal columns, right, and we have X and Y are just vectors in Rn, then we have the following. So first, if we take U and multiply it by X, and then take the norm, right? So U times X is going to give us a vector. We can take its norm and then compare that to the original vector, the norm of the original vector. So it doesn't change norms. Multiplying by U does not change the norm of that vector X, right? Okay. And it also preserves dot products in the following way. So if we took U times X and dotted that with U times Y, that is going to give you the same thing as X dot Y. Okay, so preserves dot products. So the interesting thing about preserving dot products is that that also tells us that it preserves angles in some sense, right? Because dot products give us a way to define angles between vectors. And if dot products are preserved, that tells us that the angle between vectors is preserved. So it doesn't do any, it doesn't distort angles, basically. And so in particular, if X and Y are orthogonal, so if their dot product is equal to 0, then U times X dot U times Y is equal to 0. So these are orthogonal as well. Okay, and then lastly, the determinant of U is equal to plus or minus 1. And that's not too hard to show. So let's just do it really quick. Where do we have time? Actually, we're going to skip that, but maybe try this yourself. Okay.
There's a question.
Yeah, go ahead.
So for a matrix that has orthogonal columns, the matrix itself doesn't have to be a square matrix.
No, it doesn't have to be. But if it is, so this actually leads into something. So if U is square and we look at the transformation corresponding to U, so the transformation given by U times X, then this transformation will be just a rotation. So say, then T is going to map Rn to Rn, right, if it's given by U. I guess then T is a rotation.
And that's also how you can see that the determinant is going to be 1, because it's not going to change the area of the of
Yeah.
the unit square.
Exactly, yeah. Yeah,
You can also do some stuff because U transpose times U is the identity matrix and the determinant of the identity matrix is 1.
right, yeah.
Yeah?
Yeah, that's the other
Cool.
way you can look at it. Yeah, so this is pretty, I don't know, interesting to know that we get rotations in this way. So they'll all have this form, in fact. Okay, so yeah, we have a little bit of time to go on to 6.3. So this is orthogonal. Here we're talking about orthogonal projections. And the idea here is what I was referring to earlier, where we can project onto higher dimensional subspaces. So I am going to do my best to draw a picture. Okay, so say we have a vector y in Rn, and W is a subspace of Rn. Okay, the idea is, and we'll say y is not in the subspace, so it's interesting to talk about the projection. Okay. So say we have, this is our subspace W, and we have a vector y like this. Okay, so we wanted to find the projection. And so we can imagine just geometrically what this would look like. We would project down, and then we would get some vector inside of W, right? And that is what we want to call the projection. Wait, I'll do it in different color. So the projection onto W of Y would be that vector right there, right? And how we go about defining that is based on that idea where we talked about decomposing. So right at the beginning, we talked about how we get the piece that is the projection, and then we get a piece that lies in W perp, or the orthogonal complement of the subspace, right? So we can write y as the projection of W, or sorry, the projection of y onto W plus a vector z, which is in W perp. And it turns out that this is a unique representation of y, right? And so this gives us a way to define this, right? Because the z being in W perp is defined, right? We know how to get that. And we know what y is because we start with that. And so this tells us how to uniquely define the projection of y onto W, right?
Do we know that?
Mhm.
I guess. Are we going to do something where like we create an orthogonal basis for the subspace W?
Right, yeah. So yeah, getting to that, if we do have if we have an orthogonal basis of W, then say, we'll give it a name. So be made up of vectors u1 up to uk, right? If we have this, then we have a nice formula. And so this is based on the formula that we had earlier. So if we have an orthogonal basis of W, then the projection of, I guess, y onto w is going to be y dot u1 over u1 dot u1 times u1 up to y dot uk. Which is what we had, sorry, I know I'm just scrolling back, but where is it? Right here. Yeah, what we had here for representing a vector in terms of the basis, right? So that's what we're doing here. So this projection should lie inside of the subspace, right? That's part of the definition of it. And so this tells us how to even represent it as a coordinate vector in the subspace, in the basis that you're given, right? Okay. Let's see. So what's the most important thing to mention here? Yeah, so we're gonna skip some things in this section just because we're like almost out of time. So I think that actually we're gonna skip most of this section. But this is, I guess, the most important part, right? This formula. And then in the next section, we can learn how to take any basis and turn it into an orthogonal basis, right? So we will go over that since that is very useful, and that's basically where we will end with the class. Right, so we will take the quiz in a second. The other thing that I wanted to do next time, which will be our last class, is to have you guys say, like, I don't know, a couple words about your project to everybody in the class, just so we can like get an idea of like what things were investigated. And you know, I thought it'd be kind of interesting. And then if you're interested to know more, you can go look on the discussion board and see that person's project, right? So we'll do that next time at the beginning of class because I don't know how long it will take. And then we'll just finish up with the Graham-Schmidt decomposition stuff. Great.